Hello, class. This lesson we are going to simplify identities using our fundamental identities here in this next slide. We have up to this point not used these much, but from here on out we will use these identities to help with finding values, solving trig equations from in the next few sections. And just remember that an identity, it's an equation where both sides are equal to one another. So they don't look alike, but they are the same thing. This first question wants us to use the fundamental identities to find sine if we know cosine. Well, if you look back up here, notice that pretty much all of our trig functions, like secant here, well, sorry about that. Come on now. Like secant, cosecant, tan, cotangent, and then this Pythagorean theorem identity here all contain either sine or cosine or both. So to find sine, if we know cosine, what we can do is look at these identities here and use one of them to help us find the other. So what I'm looking for is, I'm looking for an equation that contains sine and cosine and no other trig function. And that would be this Pythagorean identity here. So what we're going to do is we're going to take this identity and we're going to solve it for sine. So I'm just using algebra here. So we're going to rearrange by subtracting cosine squared theta. And that's going to give us 1 minus cosine squared theta on the right. And remember from algebra, to get rid of a square, I need sine theta, not sine squared theta. I'm going to take the square root of both sides. And remember, when you do take the square root, you have to put a plus or minus in front of it. So that gives us an identity here that we could use by plugging in what we know for cosine to find sine. So I'm going to come up here, I'm going to substitute in for cosine squared, we're going to replace it with 5 over 8, and we're going to square it. Now there's a piece of information in the question that says quadrant 4. So what do we know about sine in quadrant 4? Is it positive or negative? Well, sine is negative in quadrant 4, so we're going to choose the negative value and then begin to simplify. So all I'm doing is plugging in 1 minus parentheses 5 over 8 squared in my calculator. That gives me 39 over 64. And then I'm going to take the square root of the numerator and the denominator. 39, we're going to leave it as the square root of 39 over, and the square root of 64 is 8. So given cosine is 5 over 8, sine has a value of negative square root of 39 over 8. So the next few examples, what they want us to do here is to write each expression in terms of sine and cosine, simplify the expressions, and make sure once we simplify that no quotients appear. Remember, quotient means a fraction. So if you go back and look, remember what I said up here, that all of these trig functions can be rewritten in terms of either sine or cosine if they're not sine or cosine. So my first trig function is secant. Remember that secant is the same thing as 1 over cosine, and that cotangent, if I'm looking for cotangent, I don't want this one because that's just cotangent and tan. I want the one that has cosine or sine or both. I'm going to use this for cotangent, which is cosine over sine. So we're going to replace secant with 1 over cosine of x. All right, we're multiplying here. Cotangent becomes cosine x over sine of x. And then sine, we're not going to change it because we want it to stay sine because it says in the direction, leave it in terms of sine or cosine. If you remember with fractions, we can cross cancel. So I can cancel out cosine x with that cosine x. I can cancel out that sine with this sine because that's sine x over 1. So then the only thing, so that reduces to 1 as we substitute in those identities. So that expression, secant x cotangent x sine x, is the same thing as 1. Here, what we're going to think about is, before you start replacing anything, let's see if, before you distribute or change, let's see if this binomial here, 1 plus tan squared of x, has a value, another value. Whenever I see 1 and a trig function that's squared, I always think possibly these Pythagorean identities. So if you look here, notice tan squared theta plus 1, that is the same thing as 1 plus tan squared of x. We're just saying the angle is here, the angle is x, up here it's theta. It doesn't matter. So then it tells me that that's secant squared x. So we can actually replace the 1 plus tan squared with secant squared x. And then, now that we've replaced that binomial to a monomial, we can now replace these two with a definition in terms of sine or cosine. So we know cotangent is cosine squared x over sine squared x, and secant is 1 over cosine squared x. Notice that we are able to cancel the cosines. That's all we can do. So then I've simplified this expression, but in the directions it says no quotient. This is a quotient. What do we know? What trig function is the same as 1 over sine squared? Well, 1 over sine is cosecant. So then 1 over sine squared is cosecant squared x. So the next example, I'm looking, I see this 1, but I notice that these secants are not squared. Well, I know that's not an identity. So really the only thing we can do here is let's get rid of the parentheses by distributing. So we weren't able to get rid of it by substituting like we did up here. We can FOIL. So I'm going to FOIL this out, first, outer, inner, last. So it's secant squared x plus secant x minus secant x minus 1. Well, these were conjugates, so these are going to cancel. That's going to leave us secant squared x minus 1. Now I've got a 1 and I got a square, so let's look back here and see the Pythagorean identity that's got a secant and a 1. We're going to look at this. We can rewrite that tan squared, I'm going to, instead of theta, I'm going to say tan squared x plus 1 equals secant squared x. Look what happens if I subtract 1. I end up with tan squared x equals secant squared x minus 1, which that's exactly what we have here. So we can replace secant squared x minus 1 with tan squared x. This fourth example has cosine and sine, so I can't replace it with anything. So the only thing we can do, since it's simplified, it's already in terms of sine and cosine, we got to get rid of the quotient. Now, if you go back to algebra, what we're doing is dividing each term in the numerator by the denominator. And the denominator is a single term. So I can rewrite this as cosine x divided by sine x plus sine x divided by sine x. And then I can replace, since it's still quotients here, what is cosine x over sine x? Well, that's cotangent x. And then, of course, sine divided by sine is 1. And that is all we can do here for this particular problem in order to simplify it. So the next problem has sine and cosine. So that's good, but it's a quotient. To get rid of this quotient, I cannot divide the numerator by the denominator because my denominator is a binomial, not a monomial. 2 terms, not 1 term. So this goes back to kind of beginning algebra. In order to clear a fraction that has a binomial, we can multiply that fraction by the conjugate of the denominator. Remember, the conjugate, it's the same term but different signs. Our conjugate will be 1 minus cosine squared. So I'm going to come over here out beside, and I'm going to multiply by 1 minus cosine squared x. I'm going to do it in the numerator and in the denominator. Erase this. Come on. Erase. And we're going to fold, because it's a binomial in the numerator and the denominator, we're going to fold both of those out. So the numerator, we're going to get 1 minus no. I'm not going to fool the numerator. I'm going to leave it like it is. So let's leave it as a binomial. 1 minus sine squared x, 1 minus cosine squared x, and then fool the bottom. What I'm trying to figure out is, you'll notice as you're working, you'll see patterns develop. And I'm looking at that numerator and I'm thinking, maybe I could do some canceling. Let's fool the bottom out. So if I fool the bottom out, I'm going to get 1, well, that still doesn't work on that one. See, I worked this out, and I guess I did illegal math on this one. I'm going to come back to this one. So this is what's going to happen, and I'll fess up on these. You might try a way and find that that's not going to work. So then you have to go back and try to redo a different way and see if that would work. Well, I tell you what, let's do what I was originally going to do. Let's see what happens if we fool the numerator out. We get 1 minus, so I'm distributing 1 minus cosine squared x minus sine squared x plus sine squared x cosine squared x all over 1 plus cosine squared x. I'm going to leave it, well, we can fool that 1 minus cosine squared x. Still not seeing anything on that one. So let me skip down to this last one. All right. Here we have sine squared x plus tan squared x plus cosine squared x. So we need to change in terms of sine or cosine, and I'm going to see if we can replace with anything else. You can take these expressions and move things around. So I'm noticing something here. Sine squared x plus cosine squared x plus tan squared x. I am noticing this as a Pythagorean identity. If you look back at the identities here, notice that sine squared theta plus cosine squared theta is 1. So I can replace this with 1. Now notice we've got 1 plus tan squared theta. So I'm noticing that's a Pythagorean identity also. That's the second one here, which is secant squared theta. And that is going to be our simplified expression, since it's one term, and we've changed up what we needed to change on that one. Well, I went back and looked at the previous example, and I'm still trying to work on it. So I'm going to go ahead and finish this recording and work on it, and then I'll do an additional recording with this one problem. But typically, like I said, most of these, if you start working, you're going to see a pattern develop and things start canceling, or things start that you can rearrange to form identities. I hope this lesson is helpful. Please let me know if you have any questions.